Hey y'all, welcome back. Today we are going to learn how to take what we learned in the last lesson, which is finding all the different characteristics of rational functions, and put them all on the graph so that we can start to sketch all of these seemingly complicated rational functions. There's a couple of little tips that I want to give you just right up front before we start diving into the examples. The first one, and might be the most important one just to make the whole process go a little easier, and that is that you want to try to factor both the numerator and the denominator as much as possible. It'll help you to find the vertical asymptotes and the x-intercepts, and if you do that up front, then you don't have to worry about solving it as you're going through the process of graphing. And then the second tip I want to give you is that you may not cross a vertical asymptote, so you don't have to worry about finding points where that happens, but it is possible to cross a horizontal asymptote, so that's something we will have to check as we go. So let's take a look at the examples today, and so I can kind of show you and guide you through how to graph some of these functions.
And for all of these, what you're going to have to do is go through all the characteristics that we learned last time. So you find the x-intercepts, find the y-intercept, find the vertical asymptotes, the horizontal asymptote, and then if there's any holes, find those too, and then plot all of that onto the graph. Now before we actually start graphing these or finding any of the characteristics, you always want to try to factor first so that finding the characteristics will be a little easier. So for example, we could factor this denominator so that finding the vertical asymptotes will be a little easier. So what are the factors of x squared plus 2x minus 3? Yeah, x minus 1, x plus 3. And that'll just help us, again, find the vertical asymptotes a little easier. So right away, are there any holes in our graph? Do we need to worry about holes? Are there any x values that make both the numerator and the denominator equal 0? No. So right away we can say there's no holes. That's usually a pretty quick thing to identify right away. Okay, so there's no holes in this one. Now let's find the x-intercepts. So where's the x-intercept going to be? There's only one of them. At 0, right? It's what makes the numerator 0, so the x-intercept's going to be at 0. Now that's going to be kind of a giveaway for the y-intercept. Right? If you have an x-intercept of 0, what does the y-intercept have to be? 0. And that's what you get when you plug in 0 everywhere. You get 0 over negative 3, which is 0. Nothing more to plot there. So now let's talk about the asymptotes. So let's first find the vertical asymptotes. This will be all of the places where the function, or all the x values that make the denominator 0. So where would the vertical asymptotes be? Yeah, 1 and negative 3. So I'm going to plot those on here. X equals 1, we have a vertical asymptote. And really these lines should be dotted, but I think it'll be easier to see if I make them kind of bold like that. And then 1 at negative 3. All right. One last thing, the horizontal asymptote. So in this case, the degree on the bottom is bigger. So what does that mean in terms of our horizontal asymptote? Yeah, it's at 0. So for all the characteristics, this is all we know. Right, this is as much as we can graph on there. We should have kind of a good idea of what the graph is going to look like, but not really. We don't really know exactly where it is. So to figure out what's going on with the graph at this point, what we need to do is kind of like what we did when we were solving those inequalities, is we want to know when is the graph above the x-axis and when is it below. In other words, where is the graph positive and where is the graph negative? And that will tell us, for instance, if we have a curve that's up here or down here. Right? So this curve is either going to go like this direction or this direction. So the easiest way to do that is just like what you did with those inequalities, and that is to pick a representative from each interval and find out, is it positive or negative? So, like if I pick a number like negative 1,000, I don't know, pick some like, or negative 10 or something like that, some value that is less than negative 5, negative 3, and plug it in, what happens? Well, if I plug in negative 10 up in the numerator and get a negative, if I plug negative 10 in the denominator, what do I get? Okay, a negative. So negative 10 here would make this negative. A negative 10 here would be this negative. So negative times a negative is a positive. So between negative infinity and negative 3, is the curve going to be above or below the x-axis? You got to be below, right? So that means that I know for sure that I've got my curve right there. Now you want to be careful. The intervals are not just going to be partitioned by the vertical asymptotes. They're also going to be partitioned by the x-intercepts. So the next interval that we're going to check is actually from negative 3 to 0. And this little 0 to 1 interval will be separate. Basically what we want to know is, like, from this vertical asymptote to this x-intercept, does the graph go like that or does it go like that? So again, what would be a good representative between negative 3 and 0? Negative 1 probably makes sense. Okay, so if I plug in negative 1, I get a negative on top and a negative on the bottom. So that means that I'm going to be what? Above or below the x-axis? Above, right? This would be positive. So from this x-intercept to that left boundary, I'm going up. Then I want to check from 0 to 1. You know, does this bounce off the x-axis? We have an indication that it doesn't, right? Because that 0 doesn't have an even multiplicity. But let's just double check so that we don't want to have to memorize that. So let's say like 0.5. If I plug in 0.5, that's going to give me a positive on top and a negative on bottom. So that's going to be negative. So this is going to come down like this. Finally, this last interval, let's say we pick something like 10. That's going to give us a positive over a positive. So the last curve is going to be up here. Notice I'm not really plotting any points on this last one. That's okay. It's not a big deal. Let's do another one. I'll just like keep working here. So this one obviously is going to have a hole. Sort of a spoiler alert here. First I want to factor this. So this is going to be 5 times x minus 2 over x plus 3 times x minus 2. Now, I'm going to have a hole here, right? Where is the hole? At what x value? 2. Okay, so I know I'm going to have a hole at 2, comma something. My whole equation is going to be what I get when I cancel out these x minus 2's. So that would be like 5 over x plus 3. Not a whole lot of room to write this. So if I plug in 2, my output is what? 1. So I've got a hole at 2 comma 1, and I can actually go ahead and just plot that right away. What's nice about that is that can act as our representative from whatever interval that is. Okay, same thing with the the y-intercept. That can act as a representative too. So let's go through all the rest of it. Where are my x-intercepts? There are none. Okay, the reason there are none is there are no x values that make the numerator 0 that don't make the denominator also 0. So no x-intercepts. What's next? What about the y-intercept? If I plug in 0 everywhere, what do I get for my y-intercept? So 0, 0, 0. So that would just be like negative 6 over, negative 10 over negative 6. So 5/3, like a little bit more than 1. Where looks like there's only one vertical asymptote, and where's that vertical asymptote? Okay, negative 3. So 1, 2, 3. Now this is another bigger on bottom category, another bigger on bottom rational function. So my horizontal asymptote is going to be at 0. There's only going to be 2 intervals here, right? Because there's only one place where we have either a vertical asymptote or a 0. And we already have actually 2 representatives from that section. So I can graph at least this part, because I know that's going to be above the x-axis. And then on the left of that vertical asymptote, I want to make sure, I still need to check to see if it's going to be up here or down here. Now, most of the time, the graph will alternate, between positive and negative, but not always, so you definitely want to check. So if I plug in a number like negative 10, I get a negative over a positive, which is negative, so I know that the other part of the graph is going to be down here. Now, Aiden was asking about crossing the horizontal asymptote, and that happens. That may happen. So, let's look at this next one. X squared minus 1 is actually, when we factor it out, x plus 1 times x minus 1. So first of all, are there any holes? No holes. So there's no holes. We've got an x-intercept at 2. And we've got a y-intercept at, if I plug in 0 here, here, and here, or it might be easier to do it on this original function. Right, 0 minus 2, 0 minus 1 is just going to be at 2. It's got an x-intercept here, a y-intercept here. I'm going to have vertical asymptotes at x equals plus or minus 1. So vertical asymptote here, vertical asymptote here. And then finally, a horizontal asymptote, since the degree on the denominator is bigger, is going to be at y equals 0. So this is all we have here. All right, so we've got 1, 2, 3, 4 intervals to check. So let's start over here. If I plug in like negative 10, I get a negative divided by a positive, so that'd be negative. So I know I've got this curve down here. How do I know that I'm not crossing the asymptote, the horizontal asymptote, anywhere over here? What'd you say, Mitchell? Yeah, there's no zeros over here, so I can't cross it. All right, so I already have a representative in this middle interval. I've got the y-intercept is acting as my my representative, so I know I got to be above the x-axis here, so it's going to make like a little U shape. I don't have any zeros between here, so I can't like go down for any reason. I can't cross through the x-axis. All right, so finally we need to decide what's going on here, like between 1 and 2. So if I plug in like 1.5, that's going to give me a negative over a positive, which would be negative. So from this asymptote to this x-intercept, I'm negative. But if I plug in a number like 100, that's going to give me a positive over a positive. And so I should be above the horizontal asymptote, above the x-axis. But you want to remember that the horizontal asymptote is dictating the long-term end behavior of the graph. So if you're kind of confused, like, okay, well, I've got to be above here, how does that work? Well, what happens is you kind of come up and then you go back towards the asymptote. Now, it probably won't look like this, exactly like this on, like if you put it in your calculator. I'm exaggerating this just to kind of make a point. And really, all I want to see is that you're crossing over and then going back towards the asymptote. It might not go up that dramatically, but it will go up a little bit. Yes, sir?
What dictates how far up it goes?
All right, so down here what we'll see is that our denominator, when we set that equal to 0 and solve it, we get like a multiplicity of 2, so like a denominator with an even multiplicity. When we had x-intercepts that had an even multiplicity, what effect did that have on the graph? Like what happened when your graph came down and touched the x-axis? How did it interact with the x-axis when you had an even multiplicity? It bounced, right? So there is some kind of behavior that happens when you have an even multiplicity on the x-intercept. Well, when you have an even multiplicity on the vertical asymptote, something happens as well. Now, you don't have to put this together to be able to successfully graph these, but if you know this, it can make your graphing go a little bit faster. So here's sort of the trick, is that if your vertical asymptotes, so you set the denominator equal to 0 and solve it, and you get those vertical asymptotes. If this has an odd degree, or like if you just have a single root, like there's no multiplicity on that, then as you approach that vertical asymptote, you're going to approach it in opposite directions. This can make finding like the plus minus stuff go a lot faster, because if you know that it's going to alternate, you don't have to think about that anymore. If your denominator has an even multiplicity, so you have a vertical asymptote that basically happens twice, then the graph is going to approach the same direction. Like they'll both go down, and the sign will not change, just like the sign doesn't change when you hit an x-intercept that has an even multiplicity. So that you can always fall back on this, plus minus stuff, but if you know that extra piece, you can sort of bypass that a lot of the time. So just like a little tip there. Again, if that sort of just goes over your head, you don't really need to know that, because you can always just test each interval separately, but that's a little shortcut to help you graph more quickly. So let me kind of show you in action like what that does. Right away we can see there's no hole, so I'm going to make a little note of that. Right? My x-intercept is going to be at 1. My y-intercept, well, if I plug in 0, I get undefined. So there's actually no y-intercept. The vertical asymptote is at x equals 0, but notice that has an even multiplicity. Okay, so, oh wait, I don't know why I plotted that there. So what that means is, if I figure out where the graph is headed on one side, I'll know where it's going to be headed on the other side of that partition. And then the horizontal asymptote, we still have the denominator with the greater degree, so it's going to be at y equals 0. You can always fall back on the sign change thing, where we make a little number line and figure out where it's positive and negative in each interval. That's still going to work. But what I'm trying to show you is that there's a little shortcut here. So like if I plug in -10, right, I get a negative over a positive, which is negative, so I know I'm going to be below right here. Now I could go and check over here, but if I notice that I have an even multiplicity on that vertical asymptote, then I know that I have to be down here. Now you can always double check that. Like if I plug in 0.5, I'm going to get a negative over a positive, which is negative. So you can always just check it the same way we checked all the other ones. But again, it's just a little trick, okay, to know that. Now for this last interval, do we have an even multiplicity on this x-intercept? No. So it's not going to bounce off of here. It has to pass through. So it's going to come back down. So keeping in mind those multiplicity things, those, I don't want to call them rules, but if you are keeping track of the multiplicities of all these, then you don't necessarily have to test each interval if you know what's happening in one of them. You still could, though. Like if I plugged in 10, I would get a positive over a positive. So you can always fall back on that. But it is kind of nice if you understand the multiplicity conditions that you can just sort of like knock them all out at once. Say, okay, well, I've got an even multiplicity on this vertical asymptote, so I know that he's going to go the same direction. This is a single root, so I have to pass through, and so I don't have to think about if it's above or below. So let's try keeping those multiplicity rules in mind for this next one and see if we can graph it a little quicker. If I factor the numerator, I'm going to get 2 times x plus 1 times x minus 1. And if I factor the denominator, I get x plus 2 times x minus 2. All right, are there any holes? No holes. Okay, my x-intercepts are going to be at 1 and negative 1. If I plug in 0 everywhere, 0, 0, I'm going to get a y-intercept at 2 over 4, which is 1/2. My vertical asymptotes are going to be at 2 and negative 2. And now this is the first example where we have the degree of both the numerator and the denominator are equal. So how do I calculate the horizontal asymptote in that case?
Isn't it 2 over 1 or 2?
Yeah, exactly. So you're going to divide the leading coefficients. 2 over 1 is 2. So that's going to be my horizontal asymptote. All right, so with all this in mind, let's try to graph it without doing the whole plus minus testing. Okay? Now, these x-intercepts, do they have any multiplicity? No, like there's not an even multiplicity, so there's no bouncing going on. You're just going to go straight through, so it's got to look like this. Do either of these vertical asymptotes have an even multiplicity? No. So that means that the graph has to approach that vertical asymptote in an opposite direction on either side. So that's how I know that I'm not going to have a piece down here. It has to be up here. Another clue is that there's no x-intercept over here. So I couldn't like pass through down here. Okay, same thing goes for over here. For this next one, neither one of the numerator or the denominator is in factored form, so that's really where we want to start here. The numerator is going to factor to be x plus 2 times x plus 1, and the denominator will be x plus 2 times x minus 1. All right, so do we have a hole somewhere? Yeah, where's the hole? What's the x value of the hole? That's not, you can't see what I'm doing. There you go. Oh, is that better? Yeah. So yeah, it's going to be at negative 2 comma something. Okay, and what is going to be our whole equation that we can use to find the y value? Right, okay, so x plus 1 over x minus 1. So if I plug in negative 2 into that, what do I get? Okay, so 1/3. So that's where my hole is, negative 2 comma 1/3. Okay, so it's usually a good idea to take care of the hole first. That can help like alleviate any other issues, like when you're finding the x-intercepts and the vertical asymptotes. So speaking of which, where's my x-intercept? -1. Where is my y-intercept? If I plug in 0, 0, 0, 0, then that leaves me with 2 over -2, which is -1. All right, next up is my vertical asymptote. So where's the vertical asymptote going to be? At 1. By the way, this is going to come into play a little bit later, but I want you to notice that once we account for the whole, we can actually just graph the whole equation. Use that to kind of make things a little bit easier. It will be identical to this function except for the whole. So if you take care of the whole first, then you can just work with this simpler equation and use that to find all the different characteristics. That'll be helpful later on, but you might see that could be helpful here too. Finding the y-intercept, for instance, you just have to plug in 0 here and here, and you get the same thing. Okay, speaking of which, the degrees are the same on the top and the bottom for the whole equation and for the original one. So that indicates that the horizontal asymptote will be found by dividing the leading coefficients. So in both of these cases, you should get the same thing. You get 1 over 1, which is 1. So that means our horizontal asymptote's at 1. Okay, now that's everything we have so far. We have a total of 3 intervals to consider here. We've got the interval from -infinity to 1, the interval from 1 to 1, from -1 to 1, and then from 1 to infinity. Now, we already have some representatives from those left 2 intervals. Okay, like the whole can count as your representative. In other words, we know then that the function is not going to come back down here and cross over the x-axis or do anything weird. It's just going to go like this. Now, to try to figure out which side of this asymptote your function is on, there's 2 ways you can think about it. One is to pick a representative and find out if it's above or below the asymptote. So if I plug in 10, I get 11 over 9, which would be bigger than 1, so it'd be above here, right? So we know that the graph's going to be above here. But the other way you can kind of figure that out is by thinking about the multiplicities of the roots for the vertical asymptotes, right? So for this vertical asymptote, this x equals 1, did that have a multiplicity of 2? Did that root occur twice in the denominator? No, so it's just a single root, which means that the function is going to approach the asymptote going in opposite directions on either side. So that's another way you can tell that the graph on the right-hand side of that asymptote is going to be over here. So 2 ways you can go about thinking about that. You can always fall back on checking the signs, like just picking a representative from that interval to find out if it's above or below the horizontal asymptote. Or you can just, if you already have one of the intervals, you can use the whole multiplicity rule to find out what's going on.
So that's pretty much it for today. I hope you understand a little bit better how to take all those characteristics and plot them on the graph to make one cohesive, complete graph of these rational functions. As always, if you have any questions or want some clarification, please reach out. But otherwise, y'all have a great day, and I'll see you next time.